Bismillah ar-Rahman ar-Rahim. Today we are going to introduce a new concept, the concepts of capacitors. And I can show you here some of the capacitors that you can find in the market. And we have large capacitors, see the size here, and we have very small capacitors. Of course, it's all depend on the applications, where you want to put them. Capacitors are widely used in electrical circuits. Okay. Capacitors are used in electrical circuits. Okay, you find them in electrical circuits. They are used. They are used to store energy. They are used to store electrical energy. Okay. So we use it for storing electrical energy that we can later use it again. Okay. Okay. Electrical. Let's be more specific. Electrical potential energy. Okay. Let's be more specific, because you are going to ask, what is it? This electrical energy is electrical potential energy. Some of the applications of the capacitors. You can find them You can find them in the flash, in the photo flash units. Sometimes in your mobile, when you want to take a picture in a dark place, you have the flash, the light that comes out from your mobile to make the photo clear. And actually, these are capacitors which have been stored, where you have stored electrical potential energy, and then you use it at that moment to make we transform it into light. Some of the other applications are in computer memories, and also in the keyboard. You see the keyboard of your computer. Under the keyboard, there is a capacitor, and then each letter or each key, there is a capacitor where the distance between the plates of the capacitor changes according to the key, and that is transformed into a certain current or a voltage, and that voltage will be transformed into a letter which will appear on your screen. Another application is for tuning radios. You can see tuners here. Actually, these are capacitors where the area between the plates can change. I will show you later what do I mean by that. So they are used for tuning radio and TV transmitters and receivers. So they have a lot of applications, actually, capacitors, and mainly they are in the electrical circuits. What is a capacitor now? So application, photo flash units. In tuning, receivers and transmitters. Okay, receivers and transmitters in and computer memories. Actually, they are the RAM and so on, computer memories. Okay, so these are some of the applications. There are many other applications, but these are some of the applications. So the question that you might ask: what is a capacitor? What is it? What is it formed of? Okay, what is a capacitor? Actually, so the question, to answer this question, a capacitor is made of two conducting plates. Okay, these are plates. Okay, these are conducting plates. Be careful. They have to be conducting. Okay, so conducting plates. Okay, and you charge them with a positive charge here, Q, and the negative charge, Q, the same charge. You produce an electric field here between the plates, of course. There will be an electric field in this direction here. Okay, that's the electric field, and actually this is a capacitor. Okay, and you are storing energy here between the plates of the capacitor. You are storing energy. So this has, of course, the positive plate has a potential. Remember we talked about the concept of potential. I call it V2, and this had a potential. I call it a potential V1. And you must, my son, if I ask you the question, which plate has a higher potential, you can tell me which one has a higher potential by looking at the electric field. The electric field is toward the right, so as you move from left to right, the potential should decrease because you are moving with the electric field. So this plate here has a lower potential, lower V, and this one has higher V, okay? Higher V, okay? It's important to understand point. And the potential difference between the plates, I call it delta V, which is V2 minus V1. That's the potential difference between the plates, okay? In this chapter, or in these videos, we call this one, so we're going to call V2 minus V1, which is delta V. We're going to call it V only, okay? When I say the potential V, I mean delta V actually, okay? And this is, of course, in volts. You have to know this is volts. Volt. The units of V is volt. So I'm going to call it V, and that's it. I'm not going to write delta V every time, okay? Now, this configuration actually, if you look at a schematic diagram of an electric circuit, capacitors, they come like this. This is the symbol of the capacitor, okay? That's C. Two lines, okay? Two lines, and they are parallel lines, and they have the same dimensions, okay? Same length. However, we also have the battery. Later, we are going to use a battery, okay? That's a battery, okay? And it is like this. Two lines, two parallel lines, but one of them is what? Is bigger, longer than the other one. And we call this one E, electromotive force or battery. Sometimes you write here V, okay? The potential difference across the battery, okay? So this is the symbol for a capacitor, okay? Symbol for a capacitor. So you see, when you see in an electrical circuit, you see something like this, it means it is a capacitor, okay? Now, there is a relationship between the potential difference between the plate and the charge, okay? So let me write down here the relationship between the charge on the capacitor, Q, okay? The charge on the plate is equal C times V, the potential difference. I'm not going to write delta V here. I'm going to write V, the potential difference, okay? And the proportionality constant is a constant here. Is a constant. Proportionality constant between the charge on the plate and the applied voltage. You have to apply voltage here to charge the plates. I will show you later how. We call this is a charge on one plate. So let's write here the charge on one plate, and this is the potential difference between the plates, okay, between the plates, okay, and this is the capacitance now. That's the capacitance here. This C is called the capacitance, okay? That's the capacitance C, which depends on the geometry of your capacitor. We will see later, okay? So there is a relationship between the voltage applied, the charge on the plate, and the capacitance, okay? The capacitance is how much, actually, it tells you how much charge you can place for example, you take a room, okay? A room, it has a capacitance. How many people you can have in that room? Now, the capacitance in terms of here, it means how much charge you can, the bigger the capacitance, the more charge you can put, okay? And so on. You can see here. It's proportional. If C is large, for a fixed V, if I fix V, if C is large, means Q is charged. You put more charges in a capacitor which has higher C than charges in a capacitor which has lower C. So the bigger the C, the more charge you put for the same voltage. If you apply 10 volts, depending on the capacitance, you can put the charges. See? That's the relationship between charge and the SI units for these capacitors, of course. It has units, okay? It says so. This is Coulomb for the charge. This is volt, okay? And so SI unit for capacitance is Coulomb over what? Over volt. Okay? And this is, we call it Farad. Okay? It's another unit from Faraday. Faraday is one of the physicists. Okay? We will see later in the last chapter, we will see Faraday's law. Okay? And so on. So this is Farad. Okay? We write it like this. F. So we have what we call microfarad. Microfarad is 10 to the power minus 6 farad. Minus 6. We have picofarad. So we have nanofarad first, before let's go to nanofarad first. Nanofarad, which is 10 to the power minus 9 farad. And we have picofarad, which is 10 to the power minus 12 farad. So these are the different units. The units of capacitance is farad, okay? You have micro, nano, pico, and so on, okay? So let's write this important information here. The capacitance C does not, let me write does correctly here, does not depend on the charge or the applied voltage. Okay? It does not depend on the charge. This C does not depend on the charge or the applied voltage. It is a constant. I write it here. If you want to change C, you have to change the capacitor. You have to bring another capacitor and use it. Okay? So it does not depend on the charge or the applied voltage. So it depends on what? It depends on the geometry of your capacitor. It depends, C, the value of C here, depends on the geometry of the capacitor. Okay, so it doesn't depend on the charge or the voltage. Okay, let me now come here and show you something. Okay, let me show you here a capacitor C, and I'm going to make some changes. This is the same capacitor. I didn't change the capacitor, but I'm changing something, and you tell me, my son, what is happening here. If I apply a voltage here of 1 volt, I get a charge Q on the charge is 10 microcoulomb. Let's say we have this case. What happens if I double the voltage here? I'm going to double the voltage across the plate. I will tell you later how to double the voltage. But for the time, listen to me here, okay? What will be the charge here? The charge Q will be 20 microcoulomb. You see, you double the voltage, the charge will double. If I make the voltage here 10 volts, 10 times this voltage, the charge here will be 10 times. Q will be 100 microcoulomb, you see? So, a Q over V, which is C, is the same. It is 10 microfarad, because it is, let me show you how to get this 10 microfarad. Actually, is 10, you take this value here, 10 microcoulomb over 1 volt, it gives you 10 microfarad. If you go here, it will be 20 over 2, it gives you 10 microfarad. You go here, 100 over 10, it gives you 10 microfarad. So it is constant, right? So this is what I mean by when I say C does not depend on the charge or the applied voltage. I'm changing the applied voltage. I have different charge, but C is constant. You see here? It is a constant. Now, if I want to change the capacitor, if I want to change C, I have to bring another capacitor and do this work here, okay? So this is important fact that you should know, my son, that the C does not depend on V or Q. Depend on V or Q, the charge. Okay, it depends only on the geometry. We will see later how does this geometry goes into play here, okay? Let me now show you how to charge a capacitor, okay? Charging. Charging, okay? So you take, you charge it, you have to use a battery, okay? So you take your capacitor, okay? You put here what we call a switch, okay, S, and you put here a battery, okay? A battery, okay? So battery, B. Okay, we call it B. A battery, okay? B battery, plus or minus. So the charge here on the capacitor, Q equal to 0. On both, Q equal to 0, okay? There's no charge. We said because the switch is open, the circuit is not complete. The circuit here, the circuit is not complete, okay? To complete the circuit, you have to close the switch. So I'm going to close the switch now. I'm going to close the switch. I'm going to charge the capacitor, okay? And let me show you how this is done. So the switch now is closed. I go to my battery here, battery, plus or minus, and now something else happened, okay? Now my switch is closed, okay? Now my circuit is complete, okay? And because the switch is closed, here switch open, switch is open, and the switch is closed. So now I'm going to charge. Listen to me how you're going to charge the capacitor. My son, open your eyes here and your mind and listen to me here, okay? So my capacitor C, of course I have to put C here, capacitance. Now remember that this plate, this plate here, this plate is not, in the beginning it is not charged. It doesn't have any potential. Like here, you see this plate here, it has a charge plus, it has a potential. And this has a charge minus, it has another potential. And there's a difference in potential between the plates here, okay? Now here, in this case, this plate is not charged, and it doesn't have potential. The potential here is 0, and the potential here is high. The positive of a battery, okay? Here, we have a high potential. High potential. The positive plate of the positive terminal of the battery here has a high potential, okay? And there's no potential here, so you expect in the wire here, in this wire, there will be an electric field. And that electric field will be directed in this direction. So there will be electric field here in the wire, electric field in the wire. Now, the free particle, which are the electrons in this plate, they feel this electric field, and they start moving. Listen to me here, my son. They start moving. It's electron, which are here, the plate, they come out from the plate, and they start moving, electrons. They are going to move against the electric field, of course, because the electron, they move in opposite to the electric field, and they come to this plate here, okay? So the electron, they are coming to this plate here, and they start feeling this plate, okay? They start feeling that plate. So they are leaving this plate, and start feeling this plate. So this plate will become what? Positively charged because it has lost electrons, and this becomes negatively charged because it has gained electrons. So after some time, this plate will be plus Q, and this plate will have minus Q. Q is the number of electrons, of course, N times E. So this Q is actually N times the charge of the electron. I don't know how many electrons have traveled from this plate to this plate here. Now, when the electrons start leaving this plate and go to this plate, there will be an electric field here in this direction between the plates, okay? Like here. Electric field between the plates. And there will be a potential difference between the plates, of course, because of the electric field. Now, this flow of electrons will stop when the potential difference across the capacitor is the same as the battery. If the battery is 1.5 volts, when the potential difference here becomes 1.5 volts, the flow of electrons stops, and we say that the capacitor is fully charged. Okay? I'm going to repeat this again. Very important concept here. How you charge a capacitor. In the beginning, the charge here in the plates is 0. The switch is open. When I close the switch, there will be a potential difference between this plate and the positive. There will be an electric field in this direction, in the wire. So the electrons which are in this plate, they feel that electric field, and they start moving against the electric field, coming to this plate here. So they come to this plate. So this plate will be negatively charged because it's accepting electrons. This plate will become positively charged because it is losing electrons. And there will be an electric field between the plates. When that electric field, as you charge more the capacitor, the electric field becomes bigger, the potential difference becomes larger. when the potential difference across the capacitor and the battery are equal, if this 1.5 volt, when the potential difference here becomes 1.5 volt, the flow of electron will stop, and we say the battery is charged. Okay, sorry, the capacitor is fully charged. And then you take the capacitor and you bring it here. Now you have a capacitor with a charge here plus Q, and the charge here minus Q, and the potential difference here V, and so on. Okay, so your capacitor now is fully charged. You can use it now for storing energy between the plates here. Electric field, there will be electric field here between the plates. So there is potential energy which is stored, and I can use it later to discharge it into a lamp or something like this to get light and so on. You can change it into light and so on. Okay, and that's the application of the photo flash unit. You charge the capacitor, and then you discharge it, and then you get this flash, high intensity light, which will give you brightness in the room, and you can take pictures. Okay, so this is how you charge a capacitor. Okay, so the electrons, they flow from one plate to the other plate. Okay, so this becomes positive charge because it has lost electrons. This will become negatively charged because it has gained electrons. So this concept is very important to understand how you charge a capacitor. Okay, so thank you.